Okay, we start with essay question number 1, question 16. Okay, subjective question. I repeat the question that day we not finish. So number 1, state the conditions for equilibrium of a rigid body. So here got 2 marks. Got 2 marks means must have 2 contents. So the first content is the net force. You can say resultant force also can. The resultant force acting on the body is equals to 0. Okay, then the resultant torque about any axis of rotation is equals to 0. So this is the condition for equilibrium of the rigid body. Okay, you can write in the mathematical form also besides this one, the statement. Okay, B. A uniform rod of length L and mass M is held horizontally against a vertical wall by a light cord, making an angle theta with the rod as shown in the diagram below. So the light cord here means we can ignore the mass of the rod. Sorry, this is light cord, not rod. So the light cord, so we can ignore the weight of the cord. So we only take into consideration here for the weight of the rod. Okay, so the coefficient of static friction between the end of the rod and the wall is 0.42. So this is mu. Mu, the symbol for coefficient of static friction, 0.42. Determine the maximum value for theta if the rod is to remain in equilibrium. So all these are in equilibrium. So that means all the forces upward equals to downward, right equals to left, and then the clockwise moment equals to the anti-clockwise moment. Okay, that is what is meant by equilibrium. So the system is in static. Okay, first we determine all the forces that act on the rod. Okay, the first is tension in the string, and then we have weight of the rod, mg downward, and we have a reaction by the wall. Okay, so the reaction by the wall can be it comes from the friction of the wall and normal reaction by the wall. So from that to the reaction form in this direction. Okay, when the rod is not equilibrium, so what happen? It will sliding down at this point. So the rod sliding down, so that means the friction is opposite of the motion, so it's upward. And then normal is to the right. Okay, to the right. So the resultant from these two will give you the reaction force. Okay, so for some question, we can just say as R, or for some questions like later we will discuss, need to resolve the component of R into two component, N and the friction. Okay, then the T component is T sine theta and then T cos theta. So the T sine theta can write this in this direction here also can T sine theta, but I write here lah. Then the R just now I said normal. Okay, normal, or you can just write Rx, Ry, the component of R. So the component of Rx is normal and the component of Ry is friction. Actually, normal and friction. Okay, so we use translational equilibrium. Okay, for translational equilibriums, the upward force equals to downward force and left force equals to the right force. Or we can use direction positive for the sign, positive and negative equals to 0. So for T sine theta, upward is positive, Ry is upward, also positive here, and then mg is downward. Okay, mg downward, so it's negative. Or you can put T sine theta plus Ry equals to mg as a upward positive and downward positive force. Okay, then we rearrange this equation, becomes T sine theta equals to mg minus ry. So this is equation 1. Okay, for equation 2, we use the horizontal forces. Horizontal forces is T cos theta and Rx, which is equals to N. So Rx is to the right, T cos theta is to the left. So Rx minus T cos theta equals to 0. Or you can write as T cos theta equals to Rx. Left force equals to the right force. So this is equation 2. So for translational equilibrium, we divide into two, vertical forces and equals to 0. Sum of the horizontal forces equals to 0. Okay, for the third equation, we use rotational equilibrium. So we use moment clockwise and anti-clockwise moment. Clockwise moment and anti-clockwise moment. So altogether we have 1, 2, 3 forces. 3 forces. 1, 2, 3 forces. So make sure you have 3 terms here. 1, 2, 3. So the moment is force time distance. The two brackets here means force time distance. So the first one, let's say we choose Ry. Ry. Before that, we need to choose the fixed point. So we choose fixed point here because we are going to determine the mu. So mu, not mu, we are going to determine the maximum value for theta. And then static friction is given here with the mu 0.42. So this time, for this question, we choose the we choose the fixed point at the end here. In the previous lesson, for the same problems, we choose a fixed point at the wall here. But this time we choose fixed point at the where the cord attached to the rod here. Okay, as a fixed point. Okay, so now Ry is a clockwise moment, so therefore it's a negative sign. You put negative sign here because it's a clockwise moment. Okay, then the distance Ry from the fixed point just now is L. Let's say the rod of the length is L. So we times L. Okay, force time distance. Force must be perpendicular to the distance. And then the second one, we choose mg. So mg is downward, and for the fixed point here, it will make the anti-clockwise. For anti-clockwise moment, okay, the sign is positive. Okay, anti-clockwise moment refer to the axis of rotation in a fixed point here. So it will rotate in a anti-clockwise moment. Okay, next, the distance, the rod is a uniform rod. Okay, mentioned here uniform rod. So therefore, the weight of the rod act in the middle. So the L just now in the middle means L divided by 2 or half L. Okay, so the distance from the fixed point. And lastly, the T sine theta, you choose the vertical component or perpendicular component with the distance. So the T sine theta is on the fixed point itself. So that means it's times 0. Okay, you don't want to write this also can. You just write plus 0. So here I just want to mention that T sine theta is included actually in the equation here, but because of it's on the fixed point, so it's times the distance 0, it's become 0. Okay, now we rearrange these equations, become negative RYL plus MGL per 2 equals to 0, and RYL equals to MGL per 2. So simplify the equation. This will become equation 3. Okay, L also can be cancelled out. So equation 3. So this is the second step. Then the third step, we use simultaneous equation to solve for theta. Okay, to solve for theta, so we use simultaneous equation for these 3 equations. So first step, for the third step, okay, because we have sine theta and cos theta, we can combine this become tangent by using ratio. Equation 1 divided by equation 2, so we get t sine theta per t cos theta. On the right side, we have mg minus ry per rx. So that sine theta per cos theta, we can combine becomes tangent theta, and the t can be cancelled out. Okay, so tangent theta equals to mg minus ry per rx. Okay, now we can combine these two with equation 3. Okay, so we combine this with equation 3. So to combine with equation 3, the ry we can, because we are going to find theta, okay, and mu is given, so we substitute ry equals to mu n, okay, mu n. Because ry is the component of r, is equals to the for vertical component is equals to friction. So friction formula is mu r. So we substitute mu r. R in this case is n, n. So you substitute into here mu n. And then rx is n. Okay, the component of r. Okay, so we simplify this. Mg per n minus n can be cancelled out, so minus mu. Okay, for the equation 3, also we do the same. Substitute the ry, which is equals to the friction, and friction equation is mu n. Okay, so we bring mu to the right side, cross multiply, becomes mg per 2 mu. So we substitute this n into this equation. Okay, so mg per 2 mu, mg per 2 mu. So we substitute into n here, mg per 2 mu. Okay, minus mu. So in this equation, we can cancel out m. So what happened? The equation only have tangent theta equals to mu. So you can determine theta from here by substituting mu 0.42. So substitute mu 0.42 into the equation, so you can calculate theta. So the answer for the maximum value for theta, if the rod is to remain equilibrium, is 23 degrees. Okay. So any question on this 1B question?
Teacher.
Yeah.
Teacher, can you? Okay, Ramesh.
Yeah.
Okay, teacher, can you repeat the how to get u apa mu n from r?
Mu this one, the R here.
Yeah, ry equals to mu n.
Okay, so must remember reactions comes from combination of these two. Is the resultant. It is resultant by the friction and normal. Okay, so the Rx and Ry, the component of R is actually, Ry is actually friction, and Rx is actually normal, right, perpendicular. And because of this, that's why the reactions is in this direction. Okay? Clear or not?
Okay.
Even in other cases also. For example, friction, reaction by the later we have example also on this one, reaction. Reaction by the in the washing machine. What else? The motorcycles in a circular motion, right? By the wall. Also the reaction, all the reaction is consists of these two components. Okay, normal and friction. Reaction and normal, that's why friction usually, if you refer to certain book, friction is given by mu n actually, not written as mu r, because our books use mu r. So that's why I keep on using equation mu r for friction. Actually, the actual equation for friction is mu n, where n must be perpendicular to the surface, right? N is always perpendicular to the surface. R is not necessary, depends on the surface. If the rough surface, R must be slanting at certain angle. But if the surface is smooth, then R is equals to normal. So reaction and normal actually two different physical quantity. Clear, no?
Clear now. Thank you.
Okay. So who else just now?
Teacher, for
Yeah.
example, we assume the mg place as a fixed point. So mg becomes 0 like mg times 0. So the t sin theta will be L over 2.
Yes.
Then the negative ry will be L per 2.
Yeah. But we didn't choose at the middle here because we don't know T. T not given. So that's why we
Oh,
choose this point here because we don't know two variable. We choose in the middle here. Okay.
okay, teacher. Thank you, teacher.
Okay, so we go to the next question. Essay question, STPM 2016-17, question 18. Okay. So we do number 1A, define center of mass of a system. So center of mass of a system, 1 mark only. You can write in the mathematical form where x, the center of mass, x equals to summation of the mi times xi, and then divided by the sum of the mass, the sum of the mass, where mi is the mass of the particle and I is the distance, xi, xi is the distance of the particle from the origin. Okay. So if you use mathematical form to write definition, so you must give the meaning for the symbol used in the mathematics form equation. Okay, then 1b. 1b, three bodies P, Q, and R, okay, are connected to each other by a string which passes through two smooth pulleys as shown in the diagram below. So smooth pulley, so that's mean no friction at here. Okay. Then the mass of Q is 5 kilogram, and while the string S1 and S2 are at 55 degrees and 30 degrees respectively with the horizontal. If the system is in equilibrium, determine the tension in S1 and S2. So we are going to determine the tension in S1 and S2. So this is equilibrium state. So we use which one? We haven't one A2 haven't. So this one is for the equation one A2, not B2. A2. Okay, we go back to A2. Okay. A system consists of 2 points masses of 1.5 kg and 3.5 kg separated by a distance of 0.55 meter. Yeah. So separated by 0.55 meter. So determine the center of mass of the system. Okay, so to determine the center of mass system, we use this equation. So we choose a fixed point on 1.50 kg. You can choose here at here also. It's up to you. So anywhere. If you choose in the middle also can. So let's say I choose here at the 1.50 kg. So therefore the mean center of mass will be, okay, we have two bodies, two masses. So we use we put here two set of m times x here, so that we don't make a careless mistake lah. We have two masses, so you put two set of mass times x. So the mass here is 1.5 kg and the x is 0. Why? Because we choose fixed point here. So 1.50 kg is on the fixed point. So that's why times 0. The second one is 3.50. Mass times distance x is 0.55 from the fixed point. So The total of mass is 1.50 plus 3.50. So the solve this, you get x equals to 0.39 meter from 1.5 kg. So you must write this one because it depends on where you choose the fixed point. So if you choose the fixed point here, so that's mean 0.39 meter is from this mass, 1.50 kilogram. Okay, any problem with 1A2? Okay, so no problem. So we go to 1B. Okay, so for 1B here, we are going to determine the tension in the string S1 and string S2. So first you determine the forces. We have T1 and then T2. Okay, so we solve the component of T1. T1 cos 55 degrees and T1 sine 55 degrees. Okay, the component for T1. Then the component for T2, T2 cos 30 degrees and T2 sine 30 degrees. Okay, the rest is all PQR is weight, so it's a vertical component only. Okay, so given Q 5 kilogram, don't forget to convert to Newton. So 5 times 9.81 is 49.05 Newton. So students also always make careless mistake here. Okay, from my experience, they straight away use 5 kilogram without converting to weight, Newton, in the unit Newton. Weight, the unit for Newton, the unit for weight is Newton. Okay. Okay, now we have also tension in the string here, which is equals to the weight of the P, because all this is in equilibrium. So the tension in the string here must be balanced by the weight of P, same as R, right? The tension in the string here is balanced by the weight WR. So this tension T2 in S2 is the same as T2 here because they comes from the same string. Okay, T1 also same, this one and this one. Okay, now we use translational equilibrium. So for translational equilibrium, we choose all the horizontal forces. Horizontal forces is T2 cos 30 degrees balanced by T1 cos 55 degrees. Or you want to use T2 cos 30 degrees minus T1 cos 55 degrees equals to 0 also can. But here I straight away balance the forces left and right. If you use this method, balance the forces, horizontal forces left and right, so you don't bother about the sign. Okay, so right side, right and left you put in the different side, so you don't bother with the sign anymore. So this will reduce your careless mistake on the sign actually, using this method. Okay, so this is vertical, this is horizontal forces. So for vertical forces, upward equals to downward. Upward, we have T1 sine 55, T2 sine 30 degrees. Downward, we have 49.05 Newton. Okay, we use separate the body methods. For Q and then for P also the same. T1 equals to WP and R also the same. T2 equals to WR. Okay. So there are three bodies here. So we separate the bodies, but actually T1 is equals to WP and T2 equals to WR. So we can just use this one. Okay, so now we simplify the first equation. T1 equals to T2 cos 30 degrees per cos 45 degrees. So you get T1 equals to 1.51 T2 Newton. The unit is Newton. Okay, and the vertical forces, okay, we can substitute this T1 into here, the second equation. So 1.51 T2. Okay, so you can solve for T2. So in this equation, we only have one variable now, T2. So you can solve for T2. So the answer for T2 is 28.2 Newton. Okay, so actually what we use here is a simultaneous equation by using substitution method. Okay, so you form two equation and use simultaneous equation. Using substitution method, you get T2 equals to 28.2. And then substitute again T2 into the first equation to get T1, which is equals to 42.6. So the first question us to determine the tension in S1 and S2, which is T1 and T2 lah. So the question is answered. Okay, any problem with question 1B?
Teacher, can you repeat the part of T2?
T2?
Yes.
This one,
How? Yeah, yep.
vertical forces.
Yep.
Okay, vertical forces here. Okay, for the P, for the PQR, we can separate the body diagram. If you can remember, chapter 3, chapter 3, where we can use method separate the body, vector for vector diagram, okay, for vector diagram. So for Q, we use T sine 55 degrees plus T2 sine 30 degrees downward is equals to 49.05. For the P, T1 equals to weight of P. For R, T2 equals to weight of R. But we don't use this because the question didn't ask for weight of P. If the question asks for the weight of P, so it will equal to T1. And if the question asks weight of R equals to T2. Okay, so we don't bother about R and P, so we just refer to the Q. So T1 sine 55 degrees plus T2 sine 30 degrees equals to 49.05 degrees will be the second equation. So this is first equation, this is second equation. To solve for T1 and T2, we can use simultaneous equation. So if you want to do further calculation, let's say the question asks for weight of P and weight of R, so you can combine these three by substituting WP into the WP and WR into the above equation. So you get T1, you get the weight of P is equals to T1 and weight of R equals to T2. Okay. Any more problem for question 1B? Okay, no. So we go to question C. Question C. Okay, question C. A uniform ladder of length 4.0 meter and mass 20 kilogram is leaned against a vertical concrete wall at an angle of 40 degrees with a concrete ground. The coefficients of friction at the floor and at the wall are the same, so which is 0.45. A man of mass 70.0 kilogram climbs up the ladder and reaches point X on the ladder before the ladder starts to slip. So determine the normal reactions at the wall and at the floor. Calculate the position of point X on the ladder and between a rough floor and a rough wall, which will make the situation above safer. So we do one first. Determine the normal reaction at the wall and at the floor. So in this question, diagram is not given. So you must draw to help you to get the idea to draw the vector diagram later. So we have a wall, okay, here, and a uniform ladder. The length is 4 meter and mass is 20 kilogram. So mass angle is 40 degrees. So mass 20 kilogram at the middle. Why? How you know at the middle? Because uniform ladder. If the ladder is not uniform, the question will mention where the center of gravity of the ladder is. In this case, it's uniform, so it act at the center. So 4 meter means at the 2 meter from below end here. Okay. Okay, next, another force is from the man climb the ladder. Okay, this is the first step lah. We are going to determine the forces, all the forces that act on the ladder. Okay, the second force comes from the man. Mass of the man 70.0 kilogram. So it climbs up the ladder and reach point X. So let's say point X is here. So that's mean the weight of the man act downward, we name as WM for the weight of the man. Okay, so 70 kilogram times 9.81. We don't write here lah. If not, if I draw here, the diagram will become messy. So I wait hold on for a while. And then what else? We have friction, because the coefficient of friction given, both wall and floor is the same, 0.45. So friction at two ends. So friction at the wall here, there are two components, friction and the normal to make a reaction. Okay, it's a rough surface. So the reaction is not equals to normal. So the reaction is at a slanting angle. Okay, slanting angle. So the reaction at the floor also same. Is FR2, friction to the wall, friction on the surface, and normal. Normal always perpendicular to the surface. So the reaction will be slanting somewhere here. Okay, friction. How do you know friction direction is here? So imagine the logic where the ladder will be sliding down. So the ladder will be sliding to the left, right? So the friction must be opposite motion. So in this way. Okay, refer to the top here. Logically, the ladder will sliding downward. So that means the friction must be upward. Okay, friction always opposite of the direction of motion. Okay, not? Any problem until here? To determine all the forces that act on the ladder. Okay, so we don't use reaction here lah. It will make confused if we draw the reaction here. So no need to draw reaction. Okay, we just draw the component of the reaction given by the friction and the normal. Okay, next. So we use translational equilibrium. For translational equilibrium, for vertical forces, that's mean FR1 and N2 upward positive equals to the we put downward to the right side, so we don't bother about the negative sign because bring to the right become positive, right? So WL and WM we put on the right side. Okay, equals to WM plus WL. So this is first equation for vertical forces. So we substitute the F equals to mu N into here. So WM, I didn't put here just now, right? The calculation because it will make the diagram look messy. So I write here, WM is 20.0 times 9.81. The mass of the pen, the man is 70. So this one, mass of the man convert to weight, and mass of the ladder convert to weight. Okay, next is mu. So substitute mu 0.545 into the mu here, we get this one. And the total here is 882.9. So this is first equation. Okay, second equation from horizontal force. Horizontal forces, we have FR2. Okay, to the right. Okay, and to the left we have N1. So equals to N1. So this is horizontal forces. Then we substitute mu N2 into the friction 2 here equals to N1, and mu is 0.45 N2 equals to N1. Okay? So we are going to determine N1 and N2. So from these two equations, we solve for simultaneous equation. And you can use ratio method or substitution method. So let's say I use substitution method. So substitute N1 into the equation here. So N1 is 0.45 N2. Okay. So the equation here only have unknown N2, the variable unknown N2. So N2 equals to 734 Newton. Okay, this is N2. For N1, we substitute into here. We get N1 330 Newton. So done for the question 1. The question 1 asks to determine the normal reactions at the wall and at the floor. So N1 and N2. Okay, done. So any question for C1?
Teacher,
Yeah.
this one for the vertical forces, the upward forces equals to downward forces, am I
Mhm.
right? So it's like W, right? So for the previous question, why we didn't include the W?
Because it's equals to T1 and T2. The first question
Uh-huh.
include what the question only asks for T1 and T2. So on the way down, we already calculate the T1 and T2. We stop there lah. If you continue, you
Mm.
mean for WL lah, right?
Yep.
Hmm.
Okay. Okay, teacher.
May
Thank
I
you,
know
teacher.
who asked?
Ramesh.
Ramesh, yeah. Okay.
Okay. Thank you, teacher.
Okay. Okay. Any more question? No, So we continue with C2. C2 question is calculate the position of point X on the ladder. So point X on the ladder means here lah, I didn't write the X here, where the man climbs up the ladder and stop at this point. Okay. So for question 2, we use rotational equilibrium. Okay, rotational equilibrium. Because rotational equilibrium involve moment which is equals to force times distance. So there's a distance there. That's why we can determine the position of point X. Means the questions want the distance of point X from a fixed point. Okay. So the fixed point for rotational equilibrium here, we choose below here. Okay, the end below. So this is a fixed point, the star. Okay, so next. Okay, so we resolve the component to get all the forces perpendicular to the distance. Remember that moment is force perpendicular to distance. So that's why we need to resolve the component. So the X is along the ladder and the Y vertical component will be perpendicular to the ladder. So the N1 component will be N1 cos 40 degrees horizontally and N1 sine 40 degrees vertically. So the 40 degrees here and here is the same because they are alternate angle. Okay, alternate angle. So the component for N1 is these two. Then we do the same for component of FR1. So we need to draw the triangle this way. Okay, choose the triangle where they can make horizontal line and vertical line. Horizontal, especially the vertical line with the ladder here. So that's why we choose this triangle. Right angle triangle. Right angle triangle. Okay, so the component will be, okay, before that we need to determine the angle. So this is 40 degrees. Verticals means 50 degrees here. 50 plus 40, 90. Okay, so that's mean here is 40. Because the vertical here is 90. Okay, so 40 degrees. The component of FR1 will be FR1 cos 40 degrees vertically and FR1 sine 40 degrees horizontally. Okay, done for FR1. So we do the same for weight and weight. For weight. So weight direction is this way because weight is downward. So this is the triangle for to resolve the weight component of weight of the ladder, WL. So the angle 40 degrees here. corresponding angle. Okay, no, this is similar triangle. So this is 40 degrees. Okay, so the component will be W cos 40 degrees and W sin 40 degrees. Okay, vertical and horizontal. And for weight of the man also the same. Okay, weight of the man, WM cos 40 degrees and WM sin 40 degrees. Okay, so for rotational equilibrium, altogether, how many forces? We have FR1, N1, WL, and WM. So all 4 forces, including the N2 and FR2, they are both at the fixed point. The choose point here is a fixed point. So that means they will be times 0. So no need to dissolve their component lah, because with times distance 0, it's become 0. So we just put 0 here. Okay. If not, the diagram will become messy lah if I draw for you the component. So we just write 0 here because they are at the fixed point. So the other point, altogether there are 4 forces. So you draw 4 set of here, 4 set of force time distance bracket. I do like this. Why? Because to avoid careless mistakes. Maybe sometimes we forgot, we miss one of the force. We miss one of the force. So if you write like this, you can reduce that careless mistake. Okay, now the first one, let's say we choose WM. Okay, so we just want to choose before that. We just want to choose vertical component. So I erase all the horizontal component. So leaving all the vertical component only. Okay, so 1, 2, 3, 4. So the component that is perpendicular to the ladder only. Okay. So for WM cos 40 degrees here, the distance is, okay, it make clockwise. It make clockwise. Okay, WM make clockwise. So therefore, it's a negative sign. Okay. Then times the x distance from the fixed point is x. Okay, then another weight is WL cos 40 degrees. Also in the clockwise direction from the fixed point as a axis of rotation. So it will make clockwise moment. So the sign is also negative. Then the distance from at the center here is 2. Okay, 2 meter. Okay, and then N1 sine 40 degrees. Okay, N1 sine 40 degrees. So it will make anti-clockwise. Direction is this way, right? So for the fixed point as an axis of rotation, so it will make anti-clockwise. So it's a positive. Then times the distance. Okay, the distance N1 is at here. Okay, so distance is length of the ladder is equals to 4 given in the question, 4 meter. So times 4 meter. And lastly is FR1 cos 40 degrees. The sign is also positive because the rotation is anti-clockwise. And then the distance also 4 meter from the end of the ladder here, from the fixed point. So done for all the forces with the sign, and then we solve the equation. Okay, so we substitute the WM 70.0 times 9.81. WL is 20.0 times 9.81. And then N1 from the previous question, 1C1, we get 330. And then friction 1 is 330 mu R, mu N, so N is 330, mu is 0.45. Okay, after you substitute all the values, so you solve for X. So in this equation, we have only one unknown variable, x. So you solve for x. So the answer is 1.91 meter. From where? You must mention from the fixed point you choose just now, okay? Okay, from the bottom of the ladder. Okay, any question for C2? No, eh?
No questions.
Okay. Then we go to question 3. Okay, question 3. Between a rough floor and a rough wall, which will make the situation above safer? So the answer is a rough floor. Because if you use the rough floor, so the motion will be this way. The motion will be this way. So the friction will be this way. So if the below here is smooth, imagine this one is smooth. So how this one, the ladder slide, so it will slide totally in the immediate, you put the wall here, so immediately it will sliding down, compared to if you put if the wall here is smooth. Okay, if the wall here is smooth, the down here still manage to hold the ladder from sliding. Okay, so that the rough floor will make the situation safer for the man. Okay, compare with the a rough wall.